Look up at the night sky, and what do you see? Stars, yes, but hidden among them are vast, swirling clouds of gas and dust, glowing like celestial brushstrokes across the darkness. These are nebulae, some of the most breathtaking sights in the cosmos, but they are far more than just pretty decorations. Each one is a cosmic time capsule, its shape a carefully preserved record of the universe's past. Think of them as ancient manuscripts, written not in ink but in the language of gravity, radiation, and starlight. Every curve, every filament, every delicate tendril tells a story of stars being born, of stars dying in spectacular explosions, of forces so powerful they sculpt entire galaxies over billions of years. What if I told you these shapes aren't random, that the universe, in its own way, has a memory? It sounds like science fiction, but it's real. The swirling arms of a spiral nebula, the ghostly rings of a planetary nebula, even the jagged filaments of a supernova remnant, they all hold clues about the events that shaped them. Like detectives piecing together a crime scene, astronomers study these structures to unravel the mysteries of cosmic evolution. And the most incredible part: this isn't just about distant space. It's about our story too, because the same forces that molded these nebulae also shaped the atoms that make up you, me, and everything around us. By the time we're done, you'll never look at the night sky the same way again. You'll see the delicate tendrils of the Vale Nebula and recognize the aftermath of a star's violent death. You'll gaze at the butterfly nebula's symmetrical wings and understand how a dying star's final breaths were sculpted by invisible forces. And you'll realize that these nebulae aren't just distant wonders, they're part of an ongoing cosmic narrative, one that's still being written. So let's dive in. Together, we'll decode the hidden language of these celestial shapes and uncover what they can teach us about the universe's deepest secrets. This isn't just astronomy, it's a journey into the very memory of the cosmos itself. Nebulae are like the universe's grandest art installations, but instead of paint and canvas, they're made of interstellar gas and dust stretching across light years of space. Picture a cloud so vast it could cradle entire solar systems. Some nebulae are just that immense, but what's truly fascinating is how they light up. Emission nebulae, for instance, shine like neon signs in the cosmos, energized by the intense radiation of nearby young stars. The iconic red glow of the Orion Nebula comes from hydrogen atoms, excited by starlight until they emit that vibrant hue. On the other hand, dark nebulae, like the Coalsack Nebula, are shadowy silhouettes against the Milky Way's glow, their dense dust blocking the light from stars behind them. These aren't just empty voids, they're nurseries where future stars are quietly taking shape. The forces shaping these nebulae are anything but gentle. Gravity pulls gas and dust into dense knots, while radiation from massive stars blows bubbles and carves out cavities, like a cosmic sculptor chiseling away at marble. Magnetic fields, invisible but powerful, twist and channel charged particles into intricate filaments, creating structures that resemble delicate lace or towering pillars. Take the Vale Nebula, a supernova remnant where shockwaves have ripped through space, leaving behind a tangled web of glowing gas. Each ripple and knot in that web tells us about the explosion's energy, the direction it traveled, even the density of the surrounding interstellar medium. It's as if the universe left us a detailed blueprint of that catastrophic event. And just like detectives analyzing fingerprints, astronomers use these shapes to piece together the history of our galaxy. The Butterfly Nebula's symmetrical wings hint at a binary star system, where two stars danced so closely that their interactions funneled gas into those stunning bipolar jets. The Crab Nebula's chaotic filaments reveal the asymmetry of its supernova explosion, a blast so violent it was visible from Earth in the year 1054. Even the delicate rings of the Helix Nebula, often called the Eye of God, encode the final breaths of a dying star, its outer layers puffing away in slow, rhythmic waves. Every nebula is a snapshot of cosmic processes frozen in time, waiting for us to decode their secrets. What's remarkable is how much these structures can teach us about the universe's memory. The pillars of creation in the Eagle Nebula aren't just photogenic, they're a living record of star formation, with newborn stars eroding the very pillars that birthed them. The Tarantula Nebula's frenetic activity, with stars exploding and stellar winds colliding, shows us how dynamic these regions can be on human timescales. Even the quietest dark nebulae, like Barnard 68, hold clues about the early stages of star formation, their shapes molded by turbulence and magnetic fields we're only beginning to understand. The universe doesn't forget. It etches its history into the shapes of these nebulae, and with each new observation, we learn to read that story a little more clearly. The universe has a way of holding onto its past, not in books or hard drives, but in the very fabric of space itself. Think of cosmic memory like a celestial diary. Every event, every explosion, every birth of a star leaves an imprint, etched into the shapes of nebulae we see today. This idea isn't just poetic, it's rooted in the laws of physics. Take entropy, for example. In simple terms, it's the measure of disorder in a system, but it also carries a profound implication. Nothing in the universe is truly erased. Energy transforms, matter rearranges, but the information about those changes persists. Nebulae, with their intricate structures, are like the universe's way of keeping receipts. Consider the Vale Nebula, a sprawling remnant of a supernova explosion that occurred thousands of years ago. Its delicate filaments aren't just random swirls, they're a precise record of the shockwaves that tore through space, the density of the gas they encountered, even the magnetic fields that guided their expansion. It's as if the explosion left behind a fingerprint, and by studying its patterns, astronomers can reconstruct the moment of detonation with startling accuracy. This isn't guesswork, it's forensic science on a cosmic scale. Then there's the role of information theory, a field that explores how data is stored and transmitted. In the context of nebulae, every twist and knot in their structure encodes details about their history. The Butterfly Nebula's symmetrical wings, for instance, aren't just beautiful, they reveal the presence of a binary star system, where two stars orbited so closely that their gravitational dance funneled gas into those elegant, opposing jets. Even the faintest ripples in a nebula's glow can tell us about the radiation that shaped it, the stellar winds that sculpted it, or the turbulence that stirred it over millennia. What's truly mind-bending is how this concept stretches beyond nebulae. Black holes, for instance, were once thought to destroy information entirely, swallowing it beyond recovery. But modern physics suggests otherwise. Even a black hole's event horizon may preserve traces of what fell in, like a cosmic hologram. Nebulae, though, offer a more tangible way to study this universal memory. They're not just static snapshots, they're dynamic, evolving structures where the past is continuously written into the present. The pillars of creation, for example, aren't frozen in time. They're being eroded by the same stars they helped birth, their shapes changing in real time, adding new chapters to their story. This isn't just about understanding the past, it's about predicting the future. By decoding how nebulae retain information, scientists can model how galaxies evolve, how stars form, even how the universe itself might change over billions of years. It's like finding a key to a cosmic cipher, one that unlocks not just where we've been, but where we're headed, and the most humbling part, we're part of this story too. The atoms in our bodies were forged in the hearts of stars and scattered across the cosmos by the very explosions we now study. In a way, we're the universe remembering itself. Stars are far from passive residents of the cosmos, they're dynamic sculptors, wielding invisible tools that mold the very fabric of nebulae. Imagine a star as a cosmic artist, but instead of brushes, it uses stellar winds, relentless streams of charged particles racing outward at millions of kilometers per hour. These winds act like interstellar sandblasters, carving intricate cavities and sweeping away loose gas and dust over millennia. The result, nebulae that aren't just static clouds, but ever-changing landscapes shaped by the stars they harbor. Take the Eagle Nebula's pillars of creation, those towering columns immortalized by the Hubble Space Telescope. What looks like a serene monument is actually a battlefield, where the fierce winds from nearby massive stars are slowly but surely eroding the pillars, atom by atom. Yet even as these winds destroy, they also create pushing material into new formations, compressing gas into dense knots where future stars might ignite. This interplay between destruction and creation is written into the very shapes of wind-swept nebulae. In the Carina Nebula, for instance, stellar winds from young, hyperactive stars have blown vast bubbles, their edges glowing like celestial soap films. These bubbles aren't empty, they're filled with turbulent gas, shockwaves, and even new generations of stars triggered by the compression of surrounding material. It's a cosmic chain reaction. One star's winds shape the environment that births the next, and the clues are all there in the nebula's structure. The way a cavity curves can reveal the strength of the stellar wind that carved it. The density of a dust lane might hint at how long the wind has been blowing. Even the faintest ripples in the gas can tell us about collisions between winds from multiple stars, like interstellar traffic jams frozen in time. But stellar winds don't just shape nebulae, they also encode a star's life story. A massive star's winds change over its lifetime, starting strong and fast in its youth, then slowing as the star ages. By mapping the different layers of a nebula's structure, astronomers can essentially read these changes like tree rings. The Tarantula Nebula, for example, shows concentric shells of gas, each layer corresponding to a different phase in the lives of its central stars. It's as if the stars left behind a diary written in gusts of charged particles. Even our own sun, though modest by cosmic standards, has a solar wind that shapes the heliosphere, a protective bubble around our solar system. On a grander scale, the winds of Wolf-Rayet stars, some of the most violent in the universe, can strip away entire solar masses of material in just a few 100,000 years, leaving behind bizarre, twisted nebulae that glow with the energy of their fury. What's truly astonishing is how these processes connect across time and space. The same winds that sculpt nebulae today also seeded the universe's future. By pushing gas outward, they enrich the interstellar medium with heavy elements: carbon, oxygen, iron, forging the raw materials for planets and, ultimately, life. The pillars of creation might be slowly crumbling, but within them, new stars are forming, their own winds destined to shape the next chapter of the nebula's story. It's a reminder that in the cosmos, nothing is ever truly lost, only transformed, with each stellar breath leaving an indelible mark on the universe's memory. When a massive star reaches the end of its life, it doesn't fade quietly. It goes out in a blaze of glory so powerful it can outshine entire galaxies for weeks. This catastrophic explosion, a supernova, scatters the star's remains across space in a rapidly expanding shell of gas and dust. What's left behind isn't just chaos, it's a forensic record of the explosion itself, preserved in the intricate structures of a supernova remnant. Take the Crab Nebula, one of the most studied remnants in the sky. Its tangled filaments and swirling tendrils aren't random. They're a direct result of the supernova's shockwaves plowing through interstellar space, heating gas to millions of degrees and leaving behind a glowing, ever-expanding wreckage. What makes these remnants so fascinating is how they freeze a single cosmic moment in time. The asymmetry of their shapes, like the lopsided bubbles of Cassiopeia A, reveals how the original explosion wasn't uniform. Some parts of the star blew outward faster than others, perhaps due to internal turbulence or the influence of a companion star. Even the distribution of elements within the remnant tells a story. In Tycho's supernova remnant, astronomers have found clumps of silicon and iron moving at different speeds, tracing how the star's layered interior was violently mixed during the explosion. It's like finding shrapnel patterns at a bomb site. Each piece carries clues about the blast's origin and intensity. But supernova remnants aren't just relics of the past, they're active laboratories. The shockwaves they produce generate intense magnetic fields and accelerate particles to near light speeds, creating cosmic ray factories that bombard the galaxy. The famous Cygnus loop, for instance, glows not just from heated gas but from the high-energy electrons spiraling along magnetic field lines. These processes are so energetic that remnants can remain visible for tens of thousands of years, slowly fading as they merge with the interstellar medium. And here's the remarkable part: by measuring how much a remnant has expanded, scientists can rewind the clock. The Vale Nebula's delicate lacework, spanning over 100 light-years, suggests its explosion occurred somewhere between 5,000 and 10,000 years ago, a date that aligns with ancient human records of a guest star suddenly appearing in the night sky. Perhaps the most profound aspect of these remnants is how they seed the universe with the ingredients for new beginnings. The same explosion that destroys a star also scatters heavy elements like oxygen, carbon, and gold into space, elements that will one day become part of planets, oceans, even life itself. The Puppy's a remnant, for example, is rich with neon and magnesium, elements forged in the star's final moments. In this way, supernova remnants aren't just tombstones, they're cosmic recycling centers, transforming death into the raw materials for future stars and worlds. Their shapes, however chaotic, are a testament to the universe's endless cycle of destruction and rebirth. Planetary nebulae are the universe's way of turning stellar death into breathtaking artistry. Unlike their massive counterparts that explode as supernova, stars like our Sun meet their end with a quieter, almost poetic grace. As these stars exhaust their nuclear fuel, they don't detonate, they exhale, gently shedding their outer layers into space over thousands of years. What's left behind is a glowing shell of gas, illuminated by the star's exposed core, now a white dwarf. These shells aren't just random puffs of gas. They're sculpted into stunning, symmetrical forms, delicate rings, intricate spirals, even butterfly-like wings. The Ring Nebula, for instance, is a near-perfect circle of glowing gas, so precise it looks like a cosmic smoke ring suspended in the void. But these shapes are more than just eye candy. They're cosmic fingerprints revealing the star's hidden history. Take rotation, for example. A star spinning rapidly in its final phases can fling material outward along its equator, creating a flattened, disk-like nebula. Magnetic fields, invisible but powerful, can channel gas into twin jets, forming bipolar nebulae with hourglass shapes like the stunning Twin Jet Nebula, where two lobes of gas stretch outward like celestial wings. And if the dying star had a binary companion, that companion's gravity can stir the ejected material into spirals or clumps, leaving behind a nebula with asymmetrical knots or braided patterns. The Southern Crab Nebula, with its intricate claw-like structures, is a prime example of how a companion star can turn a star's final act into a cosmic ballet. What's truly remarkable is how much detail these nebulae preserve. The Helix Nebula, often called the Eye of God, shows concentric rings in its structure, evidence of the star puffing away material in pulses, like a candle flickering in its last moments. The Cat's Eye Nebula, with its nested bubbles and jagged jets, looks like a stellar onion, each layer representing a different episode of mass loss. Even the colors tell a story. The blue-green glow of oxygen-rich gas traces hotter regions, while the red hues of nitrogen and hydrogen reveal cooler, more distant material. It's as if the star left behind a layered autobiography written in light and gas. And here's the twist: these nebulae are fleeting. The gas expands and dissipates over tens of thousands of years, a blink in cosmic time, eventually blending into the interstellar medium. But in that short window, they offer us a front-row seat to stellar evolution. The next time you gaze at a planetary nebula, remember, you're not just seeing a dying star. You're witnessing the universe's ability to turn endings into beauty and to encode the secrets of a star's life in the delicate swirls of its final breath. Magnetic fields might be invisible to our eyes, but their influence on nebulae is anything but subtle. Picture a river flowing through a canyon. The water follows the path carved by the landscape. In space, charged particles behave similarly, guided by the unseen contours of magnetic fields that weave through nebulae like cosmic roadmaps. These fields don't just nudge particles gently, they sculpt entire structures, shaping nebulae into the intricate forms we observe. The Vale Nebula, for instance, isn't just a chaotic aftermath of a supernova. Its delicate, thread-like filaments are direct results of magnetic fields channeling energized gas into precise, swirling patterns. It's as if an invisible hand painted those wisps with meticulous care. What's astonishing is how much these magnetic imprints can reveal. By studying the polarization of light emitted by nebulae, a phenomenon where light waves align in specific directions, astronomers can trace the orientation of magnetic fields embedded within them. Take the Crab Nebula. Its chaotic web of filaments isn't just random. The way they twist and converge points to a magnetic field so intense it accelerates particles to nearly the speed of light. Even more intriguing, these fields aren't static relics. They evolve, interacting with stellar winds and shockwaves to create dynamic, ever-changing structures. In the Orion Nebula, magnetic fields act like cosmic scaffolding, supporting dense pillars of gas against the erosive force of radiation from nearby stars. Without them, these iconic formations might collapse or scatter into oblivion. But magnetic fields don't just preserve nebulae, they also leave clues about their origins. The helical patterns in some planetary nebulae, like the ethereal Spirograph Nebula, suggest the dying star's magnetic field was wound up like a spring, perhaps by a companion star's gravitational pull. Meanwhile, the vast, arc-like structures in supernova remnants hint at magnetic fields that were amplified by the explosion itself, frozen in time as the blast wave expanded. It's a cosmic feedback loop. Stars create and shape magnetic fields, and those fields, in turn, dictate how the star's material is dispersed into the universe. Perhaps the most profound implication lies in what these fields tell us about the larger cosmos. Magnetic fields permeate galaxies, influencing how gas collapses to form stars, how jets erupt from black holes, even how cosmic rays travel across interstellar space. By decoding the magnetic signatures in nebulae, We're not just studying isolated objects, we're piecing together a universal puzzle. The next time you see a nebula's delicate filaments or radiant loops, remember, you're glimpsing the hidden architecture of the universe itself, written in the silent language of magnetism. Gravity doesn't just pull, it orchestrates across the vast emptiness of space. It's the silent force that gathers scattered gas and dust into the dense, glowing tapestries we call nebulae. Picture a cosmic ballet where every particle moves in response to gravity's invisible cue, slowly collapsing into swirling eddies and towering pillars. The Orion Nebula is a perfect example. Its glowing core a nursery where gravity has compressed gas so tightly that new stars ignite like cosmic light bulbs flickering to life. But gravity's work isn't just about pulling things together, it's about balance. As gas collapses, it heats up, creating pressure that pushes back against gravity's grip. This delicate tug of war determines whether a cloud fragments into multiple stars or forms a single massive one, leaving behind a nebula pockmarked with stellar births. The fingerprints of gravity are everywhere in these structures. Take the Eagle Nebula's famous pillars. Their knotted surfaces aren't random. Each bump and protrusion marks a pocket where gravity overcame turbulence, condensing gas just enough to seed a future star. Even the wispy tendrils of the Vale Nebula, though shaped by a supernova's blast, bear the scars of gravity's earlier influence regions where denser knots resisted complete destruction, clinging together like cosmic survivors. These features aren't accidents, they're cosmic breadcrumbs leading us back to the conditions that birthed them. But gravity's story doesn't end with star formation. In planetary nebulae like the Helix, the dying star's gravity still commands the show, shaping the expelled gas into rings and spirals as it retreats inward to become a white dwarf. And in dark nebulae such as Barnard 68, gravity's slow, patient pull is quietly transforming a cold, opaque cloud into the next generation of stars, a process we can almost witness in real time as infrared telescopes peer through the dust. What's truly humbling is how gravity's rules apply universally, from the smallest nebula to entire galaxies. The same force that molds a delicate protoplanetary disk also binds galaxy clusters together, weaving a coherent narrative across scales. When we study the folds and filaments of a nebula, we're not just seeing local artistry, we're glimpsing the universe's foundational language, written in the quiet, relentless pull of mass. And with every new observation, we learn to read it a little more fluently. The Butterfly Nebula isn't just a cosmic spectacle, it's a masterclass in stellar storytelling. With its two symmetrical lobes stretching outward like celestial wings, this nebula captures a moment of perfect balance, a rare glimpse into the hidden forces that govern a star's final act. But how does something so chaotic as a dying star produce such precise symmetry? The answer lies in the star's environment. Imagine a spinning top wobbling as it slows down. Now picture that top as a star, surrounded by a dense disk of gas or locked in a gravitational dance with a companion star. As the star sheds its outer layers, that disk or companion funnels the ejected material into two opposing jets, sculpting the nebula's butterfly-like shape. It's nature's version of a carefully aimed garden hose where the spray fans out in a predictable pattern. What's remarkable is how much these shapes reveal. The Butterfly Nebula's crisp bipolar structure suggests its central star wasn't alone. It likely had a partner or a massive disk that acted like a cosmic traffic cop, directing the outflow. Without these influences, the nebula might have been a messy, uneven bubble. But here, the symmetry is so striking it almost feels deliberate. Astronomers see similar patterns in other nebulae, like M2-9, another butterfly-shaped beauty with intricate loops and knots. These features aren't just decorative, they're forensic evidence. The slight twists in the lobes hint at the star's rotation speed, while the spacing of the gas rings can reveal how often the star pulsed as it died. It's as if the star left behind a series of timed snapshots, each layer encoding a different phase of its demise, but symmetry like this doesn't last forever. Over thousands of years, the nebula's delicate wings will dissipate, blending into the interstellar medium. Yet for now, the Butterfly Nebula stands as a testament to the universe's ability to create order from chaos. The next time you see an image of this cosmic insect, remember, you're not just looking at a pretty shape, you're seeing the ghost of a stellar relationship, a farewell note written in gas and light, and a reminder that even in death, stars leave behind clues to their hidden lives. The Crab Nebula isn't just a relic of destruction, it's a living laboratory, pulsing with energy nearly 1,000 years after its birth. At its core lies a spinning neutron star, a pulsar rotating 30 times every second, blasting out beams of radiation like a cosmic lighthouse. This relentless powerhouse energizes the entire nebula, lighting up its tangled filaments in eerie blues and whites. But those filaments aren't just pretty decorations, they're forensic evidence. Each twist and knot maps the path of the original supernova's shockwave, frozen in time as it plowed through surrounding gas. The asymmetry of the nebula's shape, stretching farther in some directions than others, hints that the explosion wasn't uniform. Perhaps the star's rotation, or even a companion star's gravitational tug, skewed the blast like a firework bursting unevenly. What's astonishing is how much detail we can extract from this chaos. The crab's filaments glow with specific elements: oxygen, sulfur, hydrogen, each tracing different layers of the original star. The heavier elements, like iron and silicon, cluster in dense knots, revealing where the star's core material was violently ejected. Meanwhile, the nebula's outer edges show lighter elements, the remnants of the star's outer layers shredded by the explosion. It's like dissecting a cosmic onion, with each layer telling us about the star's structure before it died. Even the colors matter. The blue-white glow comes from synchrotron radiation, a telltale sign of electrons spiraling near light speed around magnetic fields so intense they structure the entire nebula into radiating tendrils. But the crab isn't just a static museum piece. It's still expanding, its filaments creeping outward at over 1,000 kilometers per second. By measuring this growth, astronomers have traced the explosion back to the year 1054, when Chinese and Arab astronomers recorded a guest star suddenly blazing in the sky. That historical alignment is rare and precious, letting us connect a celestial event witnessed by humans to the physical wreckage we study today. And here's the kicker: the crab's pulsar isn't just a remnant, it's a cosmic engine. Its winds collide with slower-moving debris, creating ripples and shocks that keep the nebula dynamically evolving. Yet the crab's legacy goes beyond one star's death. It's a Rosetta Stone for supernova everywhere. The processes shaping it, magnetic fields, particle acceleration, shock dynamics, are universal. When we study its chaos, we're learning how heavy elements spread through galaxies, how neutron stars influence their surroundings, even how cosmic rays bombard our planet. Every time astronomers point a telescope at the crab, they're not just observing a 1,000-year-old explosion. They're decoding the universe's playbook for stellar death and rebirth. Not all celestial wonders announce themselves with brilliant colors or dazzling light. Some of the most intriguing structures in the cosmos reveal themselves through absence, dark patches against the starry backdrop where something unseen is blocking the light. These are dark nebulae, colossal clouds of dust and cold gas so dense they absorb the glow from stars behind them, turning portions of the Milky Way into a cosmic game of connect the dots with shadow. The Horsehead Nebula is perhaps the most famous example. its unmistakable silhouette rearing against the glowing gas of Orion like a stallion frozen mid-gallop across the night sky. But these aren't just voids, they're cosmic incubators, they're encode depths hiding the earliest stages of star formation. What makes dark nebulae so fascinating is how they interact with their surroundings. Unlike their glowing counterparts, these clouds don't emit their own light instead. Their structures are revealed by what they obscure. The way their edges fray into tendrils or how they taper into sharp points tells us about the forces acting on them. Radiation from nearby stars erodes their surfaces, sculpting them into dramatic shapes, while turbulence within the cloud creates intricate internal textures. Barnard 68, a dark nebula in Ophiuchus, looks like a perfect ink blot against the stars, but infrared observations peel back its veil to show dense cores where gravity is beginning to pull material together into future stellar nurseries. It's like watching a time-lapse of a cosmic construction site with the scaffolding still in place. But dark nebulae aren't just passive obstacles. Their dust grains, tiny flecks of carbon and silicon, play a crucial role in the universe's chemical evolution. These particles act like cosmic refrigerators, radiating away heat and allowing gas to cool enough to collapse into stars. Some of these grains even carry complex molecules, the building blocks for organic compounds. The Coalsack Nebula, a vast dark smudge near the Southern Cross, is so rich with such material that future telescopes might detect the precursors to life hidden within its gloom. Perhaps the most striking thing about these shadowy giants is how fleeting they are. Over millions of years, the very stars they help create will blast them apart with radiation and winds, dissolving the darkness into glowing plasma. For now, though, dark nebulae stand as silent witnesses to the universe's cyclical nature, where today's obscurity becomes tomorrow's brilliance. The next time you spot one of these cosmic silhouettes, remember, you're not just seeing a hole in the stars. You're looking at the raw material of creation itself, waiting for its moment to shine. Turbulence in space isn't just chaos, it's a sculptor, shaping nebulae into the swirling, dynamic masterpieces we see across the cosmos. Picture a pot of boiling water where bubbles rise and collide in unpredictable patterns. Now scale that up to interstellar proportions, where entire clouds of gas and dust churn with forces powerful enough to forge stars. The Carina Nebula is a perfect example. Its towering pillars and cavernous bubbles carved by turbulent flows that operate like cosmic weather systems. These aren't gentle breezes, they're supersonic winds, colliding and twisting gas into structures that resemble storm clouds on a galactic scale. But here's the twist: turbulence doesn't just destroy. It creates. Those same chaotic motions compress gas into dense knots, triggering the birth of new stars even as they tear apart the surrounding nebula. What's fascinating is how turbulence leaves behind a kind of cosmic fingerprint. The fractal-like tendrils in the Vale Nebula, for instance, aren't random. They're the result of turbulent eddies cascading down to smaller and smaller scales, like whirlpools within whirlpools. Even the faintest ripples in a nebula's glow can reveal the speed and direction of these ancient flows, offering clues about the environment that birthed them. Scientists use supercomputers to simulate these processes, recreating the interplay of gravity, pressure, and turbulence that shapes nebulae over millennia. These simulations aren't just pretty visuals, they're time machines, letting us rewind the history of a nebula by decoding the turbulence frozen into its structure. But turbulence isn't confined to isolated pockets. It's a universal force threading through the cosmos from star-forming regions to the aftermath of supernova. In the Orion Nebula, turbulent motions stir the soup of gas and dust, preventing it from collapsing too quickly into stars. In the Tarantula Nebula, turbulence generated by overlapping stellar winds creates a frothy, ever-changing landscape where new stars ignite like sparks in a cosmic bonfire. And in the depths of dark nebulae, turbulence slows the inevitable pull of gravity, stretching out the timeline for star birth like a celestial suspense drama. The real magic lies in what turbulence tells us about the universe's memory. Just as tree rings record years of growth, the patterns etched by turbulence preserve a nebula's past, its collisions, its shocks, even the whispers of long-vanished stars whose winds first stirred the chaos. When astronomers study these swirling signatures, they're not just mapping gas and dust, they're reading a story written in motion, a testament to the universe's restless creativity. So the next time you see a nebula's intricate swirls, remember, you're witnessing the aftermath of a storm that's been raging for millions of years, one that's still shaping the cosmos today. The Helix Nebula stares back at us like a cosmic eye, its eerie glow a haunting reminder of our own sun's eventual fate. Located just 700 light-years away, practically next door in galactic terms, this planetary nebula offers one of the clearest views into how stars like ours meet their end. What makes the Helix so special isn't just its proximity, it's the intricate details frozen in its structure. Those ghostly concentric rings aren't just for show, they're the star's final heartbeat, a series of gasps where ejected layers of material at regular intervals before collapsing into a white dwarf. Imagine a tree's rings, but instead of marking years of growth, they chronicle millennia of stellar decay, each ripple a chapter in the star's slow-motion farewell. Zoom in closer, and the nebula's radial streaks come into focus like spokes on a wheel or cracks in shattered glass. These aren't random fractures. They're the scars of violent stellar winds slamming into slower-moving material the star shed earlier, creating shock waves that sculpt the gas into these razor-thin filaments. It's as if we're seeing sound waves frozen in time, a snapshot of the star's death throes reverberating through space, the blue-green glow at the nebula's core. That's oxygen atoms superheated by the ultraviolet radiation of the exposed white dwarf, while the red outer regions are cooler hydrogen, drifting away into the void. Every hue, every curve is a clue, a piece of evidence astronomers use to reconstruct the star's final acts. But the Helix has secrets buried even deeper. Recent observations reveal faint, comet-like knots peppering the nebula, each one a dense globule of gas and dust, so massive it could form an entire solar system. These aren't just debris, they're time capsules. As the dying star's radiation eats away at them, they glow like cosmic embers, their tails stretching outward like windsocks in a stellar breeze. Their very existence hints at a turbulent past, suggesting the star may have had a companion, a binary partner whose gravity stirred the pot, flinging material into these strange, sculpted clumps. What's truly humbling is how much the Helix mirrors our own solar system's future. In about 5 billion years, the sun will swell into a red giant, then shed its layers just like this, leaving behind a glowing shell and a tiny, dense core. The Helix gives us a sneak peek at that fate, not as a distant abstraction but as a vivid, unfolding process. It's a reminder that the cosmos doesn't just create and destroy, it remembers. Every ripple, every knot in this nebula is a testament to forces that shaped it, a story written in light and gas waiting for us to decode. And as telescopes grow more powerful, we're not just reading that story, we're learning to hear the whispers of the star itself. Nebulae aren't just celestial eye candy, they're the universe's ultimate physics classrooms, where the fundamental laws of nature play out on scales so vast they defy imagination. Picture a laboratory, but instead of beakers and Bunsen burners, the tools are superheated plasma, crushing gravitational forces and magnetic fields strong enough to twist space itself. Take the Orion Nebula, for instance. Its glowing core isn't just a pretty light show. It's a real-time demonstration of ionization, where ultraviolet radiation from newborn stars strips electrons from hydrogen atoms, causing them to emit that iconic red glow. This process, happening across light years, mirrors the same physics that powers fluorescent lights on Earth, just on a cosmic scale. But the experiments don't stop there. Supernova remnants like Cassiopeia are natural particle accelerators, their shockwaves hurling electrons at nearly the speed of light. These high-energy collisions generate X-rays and gamma rays, giving scientists a front-row seat to processes that would require impossibly powerful machines to recreate in a lab. And then there's the Crab Nebula, where the spinning pulsar at its heart acts like a colossal dynamo. Its magnetic fields so intense they whip particles into frenzied spirals, producing eerie blue synchrotron radiation. It's as if the universe set up a permanent exhibit on electromagnetism, free for anyone with a telescope to observe. What's truly groundbreaking is how nebulae let us test theories about turbulence, one of physics' last great unsolved problems. In the Carina Nebula, chaotic flows stir gas into fractal-like patterns, mimicking the same turbulence that shapes weather systems on Earth or even the flow of blood through arteries. By studying these cosmic whirlpools, researchers can refine models that predict everything from airplane wing designs to plasma fusion in reactors. The Vale Nebula's delicate filaments, meanwhile, are a masterclass in fluid dynamics, their twisted strands revealing how shockwaves interact with interstellar material over millennia. Perhaps the most profound lessons come from planetary nebulae like the Helix, where the delicate balance of radiation pressure and gravity crafts intricate shells and jets. These structures are natural experiments in stellar evolution, showing how stars recycle their enriched material back into the galaxy. Every element heavier than hydrogen and helium, the carbon in our bones, the oxygen we breathe, was forged in stellar cores and scattered by nebulae like these. So when we study their shapes, we're not just decoding the past, we're glimpsing the universal processes that made our very existence possible. And that's what makes nebulae more than just labs. They're the universe's way of teaching us how it works. The Orion Nebula isn't just a glittering smudge in the night sky, it's a bustling cosmic maternity ward, where stars are born in clouds of gas and dust so dense they blot out the light behind them. At its heart lies the Trapezium cluster, a group of young, blisteringly hot stars whose ultraviolet radiation ionizes the surrounding hydrogen, making the entire nebula glow like a neon sign in the void. But what makes Orion truly special is how close it is, just about 1,300 light-years away, giving us an unprecedented view of star formation in action. Those delicate filaments swirling around its core aren't just decorative, they're the birthplaces of future solar systems, where gravity is slowly pulling gas into dense knots that will one day ignite into new stars. Zoom in closer and the nebula reveals even more secrets. The dark patches peppering its bright regions aren't empty, they're protoplanetary disks, thick cocoons of dust where planets are currently forming. Some of these disks, like those in the famous Hubble images, are edge-on, appearing as tiny black slits against the glowing backdrop. Others face us head-on, their swirling material hinting at the early stages of worlds taking shape. And then there are the proplids, short for ionized protoplanetary disks, which look like comets with glowing tails, not because they're moving, but because the trapezium star's fierce radiation is literally blowing their outer layers away. It's a cosmic tug-of-war, gravity pulling material inward to build planets, while stellar winds try to strip it all away. But the Orion Nebula isn't just a passive incubator. The very stars it births are already reshaping it. Young, massive stars unleash powerful winds that carve out vast cavities in the gas, like bulldozers clearing cosmic construction sites. These bubbles, some spanning dozens of light years, trigger chain reactions, compressing nearby gas until it collapses into even more stars. It's a self-perpetuating cycle, where each generation of stars alters the environment for the next. The nebula's famous bright bar, a ridge of dense gas near the trapezium, is a perfect example. This structure isn't static. It's a dynamic front where radiation and gravity battle for dominance, creating a hotspot for future stellar births. What's astonishing is how much Orion teaches us about our own origins. The Sun likely formed in a similar stellar nursery billions of years ago, surrounded by siblings that have since drifted apart across the galaxy. When we study Orion's chaotic beauty, we're glimpsing the conditions that birthed not just distant stars, but potentially every planet and life within them. And because the nebula changes on human timescales, with new stars flaring to life and old structures dissolving, it's like watching the universe's creative process in fast forward. The next time you spot Orion's sword hanging below his belt, remember, you're not just seeing a pretty cloud of gas, you're looking at the universe's workshop, where the raw materials of existence are being forged into something new. The Vale Nebula is more than just a cosmic wreckage. It's a sprawling crime scene where every twisted filament and glowing tendril holds clues to a cataclysm that unfolded thousands of years ago. Picture a star 20 times more massive than our Sun, reaching the end of its life in a violent supernova explosion. The blast didn't just fade into darkness, it carved its signature into space, leaving behind a labyrinth of ionized gas that stretches over 100 light-years across the constellation Cygnus. What makes the Vale so mesmerizing isn't just its scale, it's the exquisite detail. Those delicate, lace-like strands aren't random. They're shockwaves frozen in time, the aftermath of a stellar explosion's energy slamming into the surrounding interstellar medium like a hammer hitting glass. The hotter regions glow in vivid blues and reds, oxygen and hydrogen atoms energized by the collision, while cooler filaments weave through them like ghostly threads. Zoom in closer, and the nebula reveals its secrets. The way certain filaments curl or branch tells astronomers about the density of the gas the supernova encountered. Tighter knots suggest denser regions where the shockwave slowed, while feathery tendrils trace paths through emptier space. Even the colors encode information. The crimson hues of hydrogen reveal where the blast wave is still heating gas, while the electric blue of oxygen marks areas where temperatures soar into millions of degrees. It's like reading a cosmic weather report, with every ripple and ripple mapping the turbulence of an explosion that occurred when humanity was first building its earliest civilizations. But the Vale isn't just a relic of the past, it's still evolving. The nebula's western arc, one of its brightest sections, shows signs of recent collisions with unseen clouds of interstellar material, creating secondary shockwaves that ripple outward like echoes. Meanwhile, the Witch's Broom, a jagged filament in the nebula's eastern edge, is expanding at over 600,000 kilometers per hour, its structure fraying as it plows into cooler gas. These dynamic processes aren't just spectacular to observe, they're teaching scientists how supernova remnants enrich the galaxy with heavy elements, scattering ingredients for future stars and planets. What's truly haunting is how this destruction birthed new possibilities. The same explosion that ripped the star apart also forged elements like iron, silicon, and neon elements that now drift through the nebula's veins, destined to one day coalesce into new worlds. The Vale doesn't just memorialize a star's death, it showcases the universe's relentless cycle of creation and destruction. And because the nebula is close enough to study in stunning detail, it serves as a Rosetta Stone for understanding supernova across the cosmos. Every time we unravel another of its threads, we're piecing together the story of how chaos gives rise to order, and how even in annihilation, the cosmos remembers. The Lagoon Nebula is cosmic theater at its most dramatic, a swirling maelstrom where creation and destruction play out side by side on a stage spanning 100 light-years. At first glance, its glowing pink hydrogen clouds and encode dust lanes make it resemble a celestial hurricane, but this is no ordinary storm. Nestled in the constellation Sagittarius, the lagoon is one of the few star-forming regions visible to the naked eye from Earth, appearing as a faint smudge even without a telescope. Peer closer, though, and the nebula reveals its true nature, a battleground where gravity, radiation, and stellar winds wage an endless tug of war. Towering pillars of gas, reminiscent of the Eagle Nebula's famous formations, rise like skyscrapers, their surfaces pockmarked with protostars still wrapped in dusty cocoons. Nearby, newborn stars ignite with such intensity their ultraviolet radiation carves vast cavities into the surrounding gas, while supernova shockwaves from expired giants send ripples through the nebula's structure. It's a place where time operates on two scales, stellar lifetimes measured in millions of years, and violent changes observable within a single human generation. What sets the lagoon apart is its sheer volatility. Unlike slower evolving nebulae, this one practically hums with activity. The bright young star Herschel 36, 20,000 times more luminous than our Sun, acts like a cosmic blowtorch, sculpting the nebula's iconic hourglass region where gas glows electric blue under its relentless radiation. Meanwhile, dark Bok globules, dense clots of dust resembling floating ink blots, drift through the chaos, shielding pockets of gas where future stars may form. The contrast couldn't be starker. Some areas of the lagoon are evaporating before our eyes, while others quietly gather mass for stellar births yet to come. Even the nebula's name hints at its duality. The lagoon moniker comes from the dark tidal channel that slices through its glowing core, a river of dust that divides the nebula like a cosmic shoreline separating two turbulent seas. But the real magic lies in how the lagoon's structure encodes its history. The twisted arcs near its center aren't random. They are fossilized evidence of past supernova, their shockwaves frozen in the act of plowing through interstellar material. The distribution of its star clusters tells another story. Older groups sit farther from the nebula's active core, like concentric rings marking waves of star formation that swept outward over millennia. Even the nebula's famous twister, a helix of dust stretching 8 light-years into space, isn't just a pretty spiral. Its shape betrays the presence of hidden magnetic fields, channeling gas into this bizarre wall like water spiraling down a drain. Every fold and ripple in the lagoon's tapestry is a sentence in an ongoing cosmic narrative, one where the ink hasn't even dried yet. What makes this nebula truly special is its accessibility, not just in distance but in witnessing change. In 2018, astronomers watched as a previously dim star near the lagoon's core suddenly flared to prominence, its outburst illuminating surrounding gas like a flashlight beam in fog. Such events are rare windows into real-time stellar evolution, proving that nebulae aren't just static snapshots but living, breathing entities. The lagoon doesn't just hold memories of the past, it's actively writing its future, with every newborn star and fading supernova adding another stroke to its ever-shifting portrait. To observe it is to see the universe's creative engine in motion, a reminder that even in the vastness of space, nothing ever stands still. The Trifid Nebula is like a cosmic sampler platter, offering three distinct astronomical phenomena in one breathtaking package. Its name, Latin for divided into three lobes, hints at the dark dust lanes that slice through its glowing heart, creating compartments where different physical processes unfold simultaneously. To the untrained eye, it might look like a simple splash of color in the constellation Sagittarius, but zoom in, and each section reveals its own unique story. The lower portion glows a fierce red, typical of an emission nebula where ultraviolet light from newborn stars ionizes hydrogen gas, causing it to fluoresce like a neon sign in the void. Just above it, a cooler blue region shines not from its own light, but by reflecting starlight off dust particles, a reflection nebula acting like a cosmic mirror. And threading through both are those inky black dust lanes, dense enough to block starlight entirely, yet porous enough to let new stars emerge from their shadowy depths. What makes the Trifid so remarkable is how these regions interact. The massive star at the nebula's core, HD 1642-9, is the puppeteer behind much of the action. Its fierce radiation ionizes the gas below, while its light bounces off dust grains to create the blue reflection nebula above. Meanwhile, the dark lanes aren't just passive dividers, they're active stellar nurseries. Infrared observations reveal hidden protostars buried within them, their gravity pulling material into dense knots that will one day ignite. It's a snapshot of three cosmic processes: creation, illumination, and obstruction, all unfolding in a single structure. The nebula even showcases how these forces compete. The very stars born in the dark lanes will eventually erode them with their radiation, carving new cavities and altering the nebula's shape over millennia. This interplay makes the Trifid a natural laboratory for studying feedback loops in space. The glowing red region demonstrates how stars energize their surroundings, while the blue reflection zone shows how light can sculpt dust without destroying it. The dark lanes, meanwhile, reveal how gravity and turbulence resist these forces, maintaining pockets where future generations of stars can form. It's a delicate balance, one that plays out differently in each lobe. The western dust lane, for instance, is thicker and more opaque, suggesting it's younger or less eroded than its eastern counterpart. The varying angles of the reflection nebula's glow indicate how dust grains are aligned by magnetic fields, offering clues about the nebula's invisible scaffolding. Even the colors tell a story. The red emission fades subtly where radiation fields weaken, while the blue reflection brightens where dust is most efficiently scattering light. But the Trifid's true genius lies in its accessibility. At just 4,000 light-years away, it's close enough for amateur telescopes to reveal its trifurcated structure, making it a favorite among stargazers. Yet professional instruments uncover layers even Hubble's famous image barely hinted at. Submillimeter telescopes detect cold gas streams feeding star formation in the dark lanes, while X-ray observatories spot young stars flickering to life within them. This combination of grandeur and intimacy makes the Trifid more than just a pretty face. It's a masterclass in how the universe weaves complexity from simplicity, proving that even in the vastness of space, the most profound stories often come in triplicate. Light echoes are the universe's way of playing tricks with time, bending our perception to reveal hidden layers of cosmic history. Imagine a star exploding like a firework in the night. Its light races outward in all directions, but some of that light doesn't travel straight to us. Instead, it bounces off dust clouds light years away, taking a detour before finally reaching our telescopes years or even decades later. These delayed reflections, called light echoes, act like celestial time machines, allowing us to study the same stellar explosion multiple times from different angles. The most famous example, V838 Monocerotes, stunned astronomers in 2002 when it suddenly flared brighter than a million suns. But the real magic came afterward. As the initial flash faded, light began reflecting off surrounding dust shells, illuminating them like a flashlight scanning the walls of a cavern. Each echo unveiled a new slice of the nebula's structure, transforming a two-dimensional image into a three-dimensional map of dust layers stretching trillions of kilometers into space. What makes light echoes so powerful is their ability to expose the invisible. In ordinary observations, dust clouds near a star often appear as flat silhouettes, their depth and arrangement lost in shadow. But when a stellar explosion's light washes over them sequentially, the echoes reveal their contours with startling clarity. It's akin to sonar in Earth's oceans, where sound waves bounce off submerged objects to outline their shapes, except here, light itself becomes the probe. The echoes from V838 Mon showed concentric shells of dust, evidence of material ejected by the star in periodic outbursts long before its dramatic flare. Without this phenomenon, those layers would have remained as hidden as tree rings beneath bark. But light echoes aren't just about static structures, they capture motion. In the case of the supernova remnant Cassiopeia A, echoes have allowed astronomers to reconstruct the explosion's asymmetry in real time. Light bouncing off dust at different distances arrives at Earth years apart, effectively creating a flipbook of the blast wave's expansion. These delayed snapshots revealed that the star didn't explode uniformly. Some regions surged outward faster than others, possibly due to interactions with previously ejected material. It's like watching a supernova in slow motion, with each echo adding another frame to the sequence. The true genius of this technique lies in its serendipity. Unlike planned observations, light echoes often surprise us, turning routine monitoring of faded stars into groundbreaking discoveries. When the red supergiant Betelgeuse dimmed unexpectedly in 2019, astronomers scrambled to determine whether it was a prelude to explosion. While the star stabilized, the event sparked searches for potential light echoes from past eruptions, ghostly signals that might still be bouncing through nearby dust, waiting to reveal Betelgeuse's secret history. What's next? As telescopes grow more sensitive, they'll catch fainter echoes from older events, potentially reconstructing stellar outbursts that predate modern astronomy. Future observatories might even use echoes to detect the remnants of supernova too distant to see directly, their presence betrayed only by reflected light. In a universe where so much is fleeting, light echoes offer a rare second chance, a way to revisit cosmic moments we missed the first time, and to read the stories written in dust we never knew was there. The Eagle Nebula's pillars of creation stand as one of the most breathtaking sights in the cosmos, towering spires of gas and dust stretching light years into the void, their silhouettes backlit by the fierce glow of newborn stars. But these iconic structures are more than just a celestial postcard. They're a cosmic paradox, simultaneously birthing stars and racing against their own destruction. The very radiation that makes them glow, the ultraviolet light from nearby massive stars, is also eroding them, atom by atom, like sandcastles at high tide. Nestled within those dusty columns, hidden from visible light, infrared telescopes reveal dozens of protostars, their gravity pulling material inward even as the external forces strip it away. It's a race between creation and annihilation, playing out in slow motion over millennia. What makes these pillars so fascinating is how they freeze a fleeting equilibrium in time. The densest knots of gas, shielded by layers of dust, resist the stellar winds long enough for gravity to collapse them into stars. Meanwhile, the outer layers are evaporating, creating the eerie, finger-like projections that give the pillars their name. Hubble's famous 1995 image captured this delicate balance, but later observations showed something startling. The pillars are changing. By 2015, comparisons revealed subtle shifts in their structures, proof that these seemingly eternal monuments are transient on cosmic timescales. Some estimates suggest they'll be completely dissolved within another 100,000 years, their material scattered into the nebula to fuel future generations of stars. Yet even as the pillars fade, they're writing their legacy into the universe. The stars forming inside them will one day ignite their own stellar winds, carving out new cavities in the surrounding gas. This cycle of destruction and rebirth isn't unique to the Eagle Nebula. It's the story of star-forming regions everywhere, but here we're witnessing it with unprecedented clarity. The pillars' intricate textures, from their wrinkled surfaces to their ghostly streamers, are like a cosmic textbook on fluid dynamics, showing how radiation and gravity sculpt interstellar material into fleeting works of art. The irony is poetic. The same forces that destroy the pillars also make them visible. Without the intense starlight ionizing their edges, these structures would blend into the dark backdrop of space, invisible to our telescopes. Their beauty is literally the glow of their own disintegration, a reminder that in the cosmos, creation and destruction are two sides of the same coin. And when the pillars are finally gone, the stars they nurtured will carry their story forward, lighting up new corners of the galaxy with the same elements that once formed those towering spires. The universe never forgets, it just rearranges itself into new shapes, each one holding the memory of what came before. The Rosette Nebula unfolds across the constellation Monoceros like a celestial blossom, its petals of glowing hydrogen gas stretching over 100 light-years wide. At first glance, this cosmic flower seems serene, but look closer, and you'll find a tempestuous nursery where newborn stars are rewriting their own birthplace. The nebula's iconic central cavity, a hollowed-out sphere of near-empty space, isn't a natural void. It's the handiwork of the massive O-type stars at its core. These stellar behemoths, some 50 times more massive than our Sun, blast their surroundings with ultraviolet radiation and supersonic winds, evaporating the very gas that birthed them and pushing it outward in a shimmering, spherical shell. It's as if the stars are gardening on a galactic scale, pruning their environment to prevent overcrowding by future generations. What makes the Rosette so special is how clearly it demonstrates stellar feedback, the process where stars regulate their own formation by altering their surroundings. The nebula's delicate filaments and globules, often called elephant trunks, are dense knots of gas resisting this erosion, their shapes sculpted by the relentless stellar winds like sand dunes shaped by desert breezes. Inside these structures, new stars are taking shape, shielded from the radiation that cleared the central cavity. Infrared observations revealed dozens of protostars hidden within these dusty wombs, their gravity battling the external forces trying to tear them apart. This balancing act between destruction and creation, radiation and gravity, is the universe's way of preventing star formation from running wild. Without feedback, a nebula like the Rosette might collapse into a single, overcrowded cluster, triggering a chain reaction of stellar births that could exhaust its gas supply too quickly. But the Rosette story isn't just about physics, it's about time. The nebula's expanding shell acts like a cosmic clock, its radius revealing the age of the central star cluster. By measuring how far the cavity has grown, astronomers estimate the cluster is roughly 4 million years old, a toddler by cosmic standards. Yet even in that short time, its stars have already reshaped their environment beyond recognition. The original gas cloud that birthed them is long gone, its material either incorporated into stars or blown outward to form the nebula's glowing petals. This transformation isn't unique. The same process birthed our own sun in a similar stellar nursery billions of years ago. But the Rosette's proximity, just 5,000 light-years away, lets us study the details with unmatched clarity. The real magic lies in the nebula's namesake structure. Unlike the chaotic swirls of many nebulae, the Rosette's symmetry is striking. Its circular form interrupted only by delicate tendrils where gas has cooled and condensed. This order emerges from the uniform push of the central star's winds, which expand outward in all directions like a balloon inflating in slow motion. But perfection is fleeting. Recent observations show the nebula's edges beginning to fray, its once sharp boundaries dissolving as the stellar winds encounter denser regions of interstellar gas. These asymmetries are clues to the nebula's future, hints that the Rosette's bloom won't last forever. Eventually, its stars will disperse, its gas will dissipate, and the flower will fade into the galactic background. But for now, it stands as a living lesson in how stars don't just inhabit the cosmos, they shape it, one stellar breath at a time. The Cat's Eye Nebula stares back at us like a cosmic enigma, its intricate layers and jagged jets defying simple explanation. Unlike the smooth rings of the Helix or the symmetrical wings of the Butterfly Nebula, this planetary nebula is a labyrinth of nested bubbles, knots, and spikes, as if the dying star at its center couldn't decide how to say goodbye. At first glance, the nebula's most striking feature is its series of concentric shells, 11 in total, each one a frozen ripple in space, marking a pulse of material ejected by the star over thousands of years. But look closer and the chaos reveals itself, twin jets shooting outward like searchlights, their paths twisted into S-shapes, while a halo of filamentary structures fans out like cracks in broken glass. This isn't just a star's gentle exhale, it's a death rattle full of fits, starts, and unexplained violence. What makes the Cat's Eye so perplexing is how its features contradict one another. The neat shells suggest periodic, orderly mass loss, as if the star sighed in rhythmic bursts. Yet the jets scream instability, their twisted forms hinting at powerful magnetic fields or gravitational tugs from an unseen companion. The leading theory, a binary star system where the dying primary star's outer layers were pulled into a disk by a smaller companion, funneling some of the ejected material into those dramatic jets. The companion's gravity could also explain the nebula's bizarre asymmetry. Its northern regions are far more complex than the south, as if something disrupted the star's final throes. It's like watching a spiraling dance where one partner's movements suddenly yank the other off balance, but the real mystery lies in the nebula's chemistry. The Cat's Eye is rich with nitrogen and oxygen, elements typically forged deep in a star's core. Their presence in the outer shells suggests the star underwent violent convulsions, dredging up material from its interior before expelling it into space. Even more puzzling are the knots, a dense globs of gas strung along the jets like beads on a string, each one a potential clue to the star's internal dynamics. Some researchers think these knots formed when fast-moving ejecta slammed into slower-moving material from earlier outbursts, creating shock waves that compressed gas into these peculiar clumps. Others propose their evidence of magnetic loops snapping like rubber bands, flinging material outward in discrete packets. Hubble's observations add another layer to the puzzle. The nebula's inner regions are expanding faster than the outer shells, implying the star's final outbursts were more energetic than its earlier ones. This isn't just a star fading quietly, it's one that went out with a series of bangs, each louder than the last. The cat's eye doesn't fit the standard models of planetary nebula formation, and that's precisely what makes it invaluable. Like a Rosetta Stone for stellar death, its contradictions force us to rethink how stars like our Sun might behave in their final moments. Every bizarre filament, every misaligned jet is a challenge to our assumptions, a reminder that the universe's farewells are rarely as simple as they seem. The Tarantula Nebula doesn't just sparkle in the night sky it roars. Nestled within the large Magellanic Cloud, a satellite galaxy orbiting our own, this colossal stellar nursery is a frenzy of creation and destruction on a scale that dwarfs anything in the Milky Way. Spanning over 1,000 light-years, its swirling clouds of gas and dust are lit from within by clusters of young stars so massive and hot, their ultraviolet radiation ionizes the surrounding hydrogen, painting the nebula in vivid shades of pink and red. But what truly sets the Tarantula apart is its sheer violence. Here, stars aren't just born, they explode, collide, and reshape their environment in real time, turning the nebula into a cosmic palimpsest where new stories are constantly being written over old ones. At the heart of this chaos lies 30 Doradus, a star cluster so dense it defies imagination. Some of its members are behemoth stars like R136A1, over 200 times the mass of our Sun, blazing with the intensity of nearly 9 million suns combined. The winds from these stellar titans tear through the nebula at speeds exceeding 1,000 kilometers per second, carving out vast cavities and triggering shockwaves that compress nearby gas into new generations of stars. It's a self-perpetuating cycle. Each stellar birth clears space for more to form, while each supernova scatters heavy elements that will one day coalesce into planets or even life. The Tarantula's structure, with its intricate web of filaments and bubbles, is a living ledger of these interactions, a record of stellar activity that updates daily. Yet the nebula's most startling feature is its impermanence. Unlike slower evolving nebulae, the Tarantula changes visibly within human timescales. In 1987, a supernova erupted on its outskirts, SN 1987A, the closest stellar explosion observed in centuries. Its shockwave is still expanding, heating the surrounding gas and leaving behind a debris field that glows in X-rays. Meanwhile, Hubble and other telescopes have captured protostellar jets punching through the nebula's dust clouds, their paths bending under the influence of turbulent magnetic fields. Even the nebula's famous starburst clusters like Hodge 301 show signs of disintegration, their stars drifting apart under gravitational tugs from nearby gas clouds. This isn't just a snapshot of star formation, it's a high-definition film, with every frame revealing new details about how cosmic environments evolve. What makes the Tarantula truly extraordinary is how it challenges our understanding of stellar nurseries. In most nebulae, star formation is a slow, stately process. Here, it's a free-for-all, with stars forming in packed clusters so dense they resemble globular clusters in their infancy. The nebula's chemistry is equally extreme. Its gas is pristine, lacking the heavy elements that pepper similar regions in the Milky Way, offering a glimpse into how stars might have formed in the early universe. And because it's far enough away to observe as a whole, yet close enough to resolve individual stars, the Tarantula serves as a bridge between studies of distant galaxies and our own galactic backyard. The next time you gaze at this cosmic tempest, remember, you're not just seeing a nebula, you're witnessing the universe's creative engine at its most unrestrained, a place where the line between chaos and creation blurs, and where every glowing tendril is a sentence in an epic still being written. The Tarantula doesn't just hold memories, it's making them right before our eyes. The future of nebula studies isn't just about sharper images or bigger telescopes. It's about learning to read the universe's diary in entirely new ways. Right now, we're standing on the brink of a revolution where instruments like the James Webb Space Telescope are peeling back layers of cosmic history with unprecedented clarity. Imagine Webb's infrared eyes piercing through the dust veils of nebulae like the pillars of creation, revealing hundreds of previously hidden protostars tucked within their folds. These observations aren't just adding detail, they're rewriting our understanding of how stars form in turbulent environments, capturing processes that were once too faint or obscured for even Hubble to detect. But Webb is just the beginning. Upcoming missions like the European Extremely Large Telescope, with its 39-meter mirror, will dissect nebula chemistry in real time, identifying complex organic molecules swirling in stellar nurseries, molecules that could one day seed life on distant worlds. What's truly transformative is how these tools will decode the subtleties of nebula shapes. Take the Helix nebula's mysterious knots. Future spectrographs will map their motion in 3 dimensions, tracing how the dying star's winds sculpted them over millennia. Algorithms powered by machine learning will sift through petabytes of data, spotting patterns in the chaos like how certain filament arrangements correlate with magnetic field strengths, or how shock waves from supernova propagate through different gas densities. These aren't just technical feats, they're keys to unlocking the physics that govern nebulae across the universe. Simulations, too, are leaping forward. Exascale computing will model entire nebulae at resolutions finer than ever before, recreating the interplay of radiation, gravity, and turbulence down to scales of light days. Picture virtual laboratories where we can rewind time to test theories like how a binary star's gravity might twist a planetary nebula into a spiral, or how dark matter's invisible pull could subtly warp a supernova remnant's expansion. Yet the most profound advances may come from unexpected corners. Citizen science projects are turning millions of volunteers into nebula detectives, crowdsourcing the discovery of rare structures in archival data. Meanwhile, radio telescopes like the Square Kilometre Array will probe the cold, dark reaches of nebulae where optical telescopes see nothing, unveiling the birthplaces of stars before they ignite. And let's not forget time-domain astronomy, the study of how celestial objects change over time. By monitoring nebulae year after year, we're catching flickers and flares that hint at unseen companions or sudden stellar outbursts, turning static snapshots into dynamic narratives. The ultimate goal, to piece together a universal shape language for nebulae a Rosetta Stone that lets us translate their forms into histories. When the next generation telescopes peer at the Tarantula Nebula's firestorm of star formation, they won't just see chaos, they'll decode the timeline of its stellar generations. When they examine the Crab Nebula's tangled filaments, they'll reconstruct the precise moment of its explosion down to the nanosecond. This isn't just about satisfying curiosity. Nebulae are cosmic clocks, yardsticks, and almanacs. Their shapes hold clues to the universe's expansion rate, the distribution of dark matter, even the conditions that made life possible. Every spiral, every jet, every shadow is a sentence in a story that began billions of years ago. And with each technological leap, we're not just reading that story, we're learning how to write the next chapter ourselves.